In section 10.8, we're going to look at a very specific type of power series called a Taylor series, and then a very specific type of Taylor series called a Maclaurin series. So a Taylor series is a way to represent or approximate a function with a power series, and it's using a function and its derivatives. And it says here, let f be a function with derivatives of all orders. So we can just continuously differentiate this function. A is a point inside the interval where the function is differentiable. And then we can create a Taylor series. It's going to be the kth derivative of f of a over k factorial times x minus a to the kth power. And k runs from 0 to infinity. So the first one is just going to be f of a, then it'll be f prime of a times x minus a, plus then we're looking at the second derivative of f of a over 2 factorial times x minus a squared, and so on. That's the Taylor series. This Taylor series is going to create a polynomial that can be used to approximate a function, and I'm going to look at a couple examples of this in just a moment. But we can take this Taylor series, and when a is 0, we can turn it into what's called the Maclaurin series. So this is just a specialized version of the Taylor series, again, where our a value is 0. So we end up having f of 0, f prime of 0 times x, second derivative of, at 0 over 2 factorial x squared. So again, it's the same thing. It's not like a completely different series. It's just the Taylor series, but with a equals 0. So like I mentioned before, the Taylor series and a Maclaurin series can be used to approximate a function. Sometimes we have functions that might be too difficult to look at in other ways, so it might be easier to use these Taylor series to approximate them. But here is just an easy example here, just to show you how this works. If we are looking at the function f of x equals e to the x, which is kind of in this teal blue color here, is the actual graph. The Taylor polynomials, we call them Taylor polynomials of order n, can be used to approximate this function. So you can see as the series or the partial sums get a little bit more elaborate, a little bit longer, the approximations are going to get closer and closer to the actual function. So the Taylor polynomial, which of order 1, which is just the first two terms of the Taylor series there, is just 1 plus x. That's this red line. So it's, at x equals 1, it hits it on the nose, but beyond that, it's not a good approximation. As we look at the Taylor polynomial of order 2, which is going to be the first 3 terms of the Taylor series, we're looking at this green line. So you can see it's getting closer. We move to the Taylor polynomial of order 3. So now we have the first 4 terms of the Taylor series. That's in yellow. So you can see it's ever getting closer to approximating the actual function, and that's the purpose of these. I have a second example here, which are approximating the function y equals cosine x, which again is kind of in this teal blue color. So you can see this one has Taylor polynomials up through order 18. You can see as the order progresses, the approximations are going to get closer and closer and closer to the actual function. So again, that's what these Taylor series are designed to do, and these Taylor polynomials are designed to do. They're designed to approximate a function. So let me show you what an example would look like. We're going to find Taylor polynomials of orders 0, 1, 2, and 3. So we're going to find 4 polynomials here in total. Now, before I find the polynomials, I just want to, on the side, look at some of these derivatives. So f of x is 1 over x, and we're looking at a equals 2. Now, f of x is 1 over x, which can be rewritten as f of x, there we go, is equal to x to the negative first power. And I'm going to need the first 3 derivatives of this. So f prime of x, that first derivative, is going to be negative x to the negative second power. The second derivative, when I bring this negative 2 in front, it's going to create a positive 2, but then x to the negative third. And then the third derivative is going to give us negative 6x to the negative fourth. So now we're going to use this to find the Taylor polynomials of orders 0, 1, 2, and 3. The Taylor polynomial of order 0 is the easiest. So we're doing this at at a equals 2. So for order 0, we're just looking at f of 2. So if you come back here, it's just f of a. So plugging into that f function, we just get 1/2. So now the Taylor polynomial of order 1 it's going to be the Taylor polynomial of order 0, which is the f of 2. And then the next term is going to be the first derivative of f at 2 times x minus 2. Well, f of 2, we've already found it. It's 1/2. The first derivative evaluated at 2 is going to be negative, and this is 1 over x squared, so it'll be negative 1/4 times x minus 2. Continuing, the Taylor polynomial of order 2, it's going to share the same first 2 terms of this as the Taylor polynomial of order 1. So we're going to have the f of 2 plus f prime of 2 times x minus 2. And then this one's going to add one more term. It's going to now have the second derivative evaluated at 2 over 2 factorial times x minus 2 squared. So the first 2 terms are going to equal 1/2 minus 1/4 times x minus 2. Now we're going to look at the third term. So f to the second derivative of 2. So we're over here. So it's going to be 2x to the negative third. That's the same thing as 2 over x cubed. So I'm going to do this to the side here. So it's 2 over 2 cubed. So that's just going to equal 2 over 8, or 1/4. So my numerator is 1/4, and it's going to be over, 2 factorial. Well, 2 factorial is just 2. So we have 1/4 divided by 2, so that's going to give us 1/8. And then x minus 2 squared. Now, the last one here for this example, it's the Taylor polynomial of order 3. Again, it's going to have the same first three terms, and then we're going to add one more term onto it. So it's still going to be evaluated at f of 2, and then we're going to look at the first derivative of 2 times x minus 2. And then we'll look at the second derivative evaluated at 2 over 2 factorial times x minus 2 squared. And I'm only writing all this out for example's sake. If you were doing this, I probably would not recopy all this. I'd just go with what the answer was before. So now we need to add our last term here. So we're going to look at the third derivative evaluated at 2 over 3 factorial times x minus 2 cubed. First three terms we've already worked out. So I'm just recopying those. And now we're going to look at this last term. The third derivative is negative 6 times x to the negative fourth. So that's negative 6 over x to the fourth. So if we look at the third derivative of 2, it's negative 6 over 2 to the fourth power, and 2 to the fourth power is just 16. And before I even worry about reducing here, I need to make note that this fraction is going to be divided by 3 factorial, which is 3 times 2 times 1, or 6. So I'm going to take negative 6/16 and divide it by 6. So that just gives me negative 1/16. And then that's going to be multiplied by x minus 2 cubed. So you can see here how these Taylor polynomials are growing longer as we continue with them. But each one, as we continue with the successive orders, are going to give us an approximation closer and closer and closer to the original function.